Good afternoon, everyone. Well, actually, still good morning, and for Rod, a very good early morning sort of thing. So, thank you very much for taking the time out of your busy day to, come and present to us. So, this is Rod Dyson, ladies and gentlemen, and he's presenting on 4H AI driven insights. So, he's going to talk to us about it from his perspective, and how it links to the mainframe and what we can all learn from him. So, thank you, Rod, and take it away.
Great. Thank you. Appreciate that. And so, yeah, good morning, good afternoon, good evening, wherever you are today. As was said, my name is Rod Dyson, Senior Director of Software Engineering at Rocket Software. I'm responsible for one of our performance monitor lines at the company. Recently we've been investigating the use of machine learning for monitoring IT systems, and especially these days in a hybrid IT environment. So what I wanted to do today was to share with you some of what we've learned about how to monitor and some of the issues that you might face when you're monitoring your systems. I know that many of you may be looking at different ways to monitor what's going on in your mainframe and cloud environments and the activity that's going on your systems. You may be using tools like Elastic and Splunk, or even just spreadsheets to look at the data, analyze it, and understand what's actually happening in your systems. So I wanted to, discuss some of the caveats that we've encountered that we know are going to be issues as you're going through this, and maybe look at a few techniques that you might be able to use to help you on your journey. So, so the first thing we want to talk about is let's just discuss what is a hybrid IT environment. This is an environment that includes the mainframe along with cloud services, cloud applications running in the cloud that access the data that's stored on the mainframe. We still have a tremendous amount of data on the mainframe. That's where the bulk of the financial institutions, insurance companies, et cetera, store most of their data. It's been collected over decades. It's sitting there for us to use. And so the applications that are being written to run in the cloud are still accessing those systems. So there's many different real world applications that are using the mainframe data, as I mentioned, the various customer service portals, that are going to access to real time to policy information. Many of us are using online banking systems these days. We have the access to our accounts. We can deposit money, take out money, look at the queries for how much money we have in our accounts, make sure that we're current on that. Insurance companies are using it for claims processing. Whenever something happens, you go online, you submit your claim there, and it's going to the mainframe, pulling the data and presenting that to you and saving the data on the mainframe as well. And more we're moving towards mobile applications too. So you can access these cloud services, which are using mainframe applications to do whatever you need to do, including the banking and the insurance and other financial institutions as well. And many companies are looking at the hybrid IT environment for data analytics and business intelligence. They're using the cloud-based analytics on those platforms to look at various trends, customer behaviors. And again, all of that is moving from cloud onto mainframe and back and forth. There are products out there that are now backing up data to the cloud. So data that exists on the mainframe is being able to be moved into the cloud for safe storage and recovery at some later time. So there has been over really the last couple of decades this huge move, to leverage what the mainframe does best with security, high volume throughput, et cetera, with more non-mainframe applications accessing that data. So that's what we're talking about when we say hybrid IT environment. And so we have to look at some of the challenges that this brings to us in this space. So you could have an e-commerce platform that's having some downtime problems, and that's affecting customers and frustrating customers, et cetera. So what do we need to do? Well, we need to detect these patterns that are leading up to it. So we want to try to predict when we're going to have some outages and prevent those if we can. So we're going to use some of these techniques we're talking about today. That's going to be able to keep our customers happy and keep our business moving. Another challenge is the online banking system that has unusual spikes. These are spikes that aren't planned for. We know that in an online system, there are going to be periods of high activity and periods of lower activity. There's a difference between what happens at 9 o'clock on a Monday morning versus 9 o'clock on a Friday or Saturday evening, when people are out and moving around doing things, not necessarily sitting in front of their desk at work. So when we see these unusual spikes, what we need to do is identify them, identify the anomalies, and try to do some root cause analysis to understand what's causing those, so that we can prevent that and smooth out the spikes, keep things running smoothly. So we also have, another platform here that might be having, downtime during peak shopping hours. Again, this is another case where we're looking at patterns and we're trying to be predictive and understand, how to prevent these outages from occurring. And finally, sorry, am I going backwards? I'm sorry, I'm going backwards. We have the records, your medical records and whatnot, and even your financial data that may be stored online. We want to be able to keep that protected. All right. We need to make sure that there's no unwarranted access to that data. And so to do that, we can look for different access patterns, access behaviors. We're looking for a high incidence of activity on a system that's unexpected, right? And then we want to be able to notify security. We want to be able to shut down any of that access that should not, be happening, so we can protect that data. Okay. And then we need to look for patterns that are affecting the availability, caused by too much uploads, too many downloads, things that are abnormal activity on the system. Again, trying to protect the system, excuse me, and keep things moving. So, we need to look at what we have been doing, what we need to do, and where we want to go. You know, mm, Einstein, it was brilliant, and as he said, you can't solve a problem using the same thinking that you used to create the problem. So traditional monitoring methods, while they are good and they can let you know when maybe certain transactions, specific one-off instances have, some problems, some degradation. They're not working very well. We need to rethink the way that we're looking at, our applications and monitoring. And there's a broader class of knowledge that we need, than we have, traditionally. So the traditional ways of monitoring the systems just aren't really going to work in the modern world, where we need to be much more proactive, much faster, in terms of response to what we see happening on our systems. And that's where some of the AI and the machine learning revolution comes into play. So, with artificial intelligence, we can be better at predicting, activity on the system. We can look at indicators that are going to give us some insight into, what might be happening in the near future. I don't think we can go very far out into the future unless we're just looking at capacity planning and trending. But what we're trying to find out is when things are starting to degrade, catch them early so that we can fix them and protect the system, keep things running smoothly. Also, we need to be able to be very broad in our monitoring. Traditionally, monitors on systems have been siloed in their tech areas, whether it's for DB2 or CICS or IMS or ZOS. They're fairly, siloed in that sense. What we need to be able to do is monitor holistically across all the mainframe plus the cloud, and the network in between, so that we can, ensure that we have a stable and well operating productive system. And we want to be able to do this automatically. We don't want people sitting in front of a monitor, watching what's going on in the system, trying to look for things. It's much better if we can have the system monitor itself. And there are obviously some caveats with that, some concerns, because we don't want to use all of the system to monitor the system. So we're going to need to look for ways of doing this very effectively, efficiently, and thoroughly as well. And then the other part we need to keep in mind is that the system is constantly evolving and changing. We have new work coming in. We have hardware upgrades. We have, different network times. We have, different seasons that come into play, whether it's, early, if it's wintertime versus, midsummer, can make a big difference in what we're doing, on the systems. And what we want to be able to do is keep our analysis, of our performance indicators as dynamic as possible so that we don't have staleness in the data that we're looking at. We're keeping current, it's going to be much better to predict if the data that we have is much more recent. So things that we want to look for is understand, one of the main things that we're interested in with computers is the amount of workload throughput that we're able to achieve. The goal of performance management is to optimize how much work gets done on a system in any given unit of time. So the way we want to think about that is to look at the key performance indicators on the systems. Okay, key performance. We're not going to track everything. There are most monitors these days. The OmegaMon for one, TMon for another, and some of the other monitors out there, whether it's MainView or whatever, are looking at thousands and thousands of metrics, and it's far too many to keep track of. And most of them, quite frankly, don't really matter to the performance of the system. So we want to look at our key performance indicators, identify those, and then focus on those. That gives us a much smaller base of numbers to be concerned with, to compute and follow the changes and the usage of those systems. Okay, we want to use those KPIs as a benchmark for monitoring. So we can take a KPI and we can create a foundation, a baseline that tells us what a normal execution behavior might be. And then we can look as that changes over time. And there's various different insights we can gain from that. So one is that we can identify when things change. And secondly, I'm sorry, in terms of performance, short-term, near-term performance problems with particular transactions. Or we can also see when the evolution of the work is moving away from the expected baseline that we had in the past. So by focusing on the throughput, we're able to tell that the system is performing healthy. We can start to identify areas that might need improvement by starting with that and the KPIs and then working down to look at other metrics after that. And it's easy to integrate all this into the artificial intelligence. The AI methods that we're going to be using, we're going to be talking about some today, are going to be very, very helpful in keeping track of all of these metrics. Okay, so what are some examples of looking at throughput? For a McKix region, we're looking at transaction response time and transaction rates. Are we getting the expected number of transactions per minute through the system that we have in the past or that are meeting our service level agreements? Do we know that we're operating as effective as we can be? Are the transactions completing in the time that they should be completing in? Okay. And again, we're looking at these things as an aggregate, not as an individual, any one transaction, but over the course of all the transactions running in that minute, are we achieving the goals that we have for our system? Are we having too many transaction events? We can track that. We can see that those are happening. That's going to have an impact on the amount of data that we can get through the system as well, right? From a database perspective, say for DB2, we're trying to look at the thread completion time. Are the threads completing quickly? Are they being responsive to and replying back to the transaction with the data that they've collected? Okay. Are there too many database rollbacks? It's the database equivalent of an append in a way. So if we have too many rollbacks, if there's problems with the applications that are causing the data to need to be rolled back instead of committed, that's going to have a serious impact on our ability to do more work on these systems. But by focusing on these KPIs alone, we can tell whether our work is actually being completed in an orderly fashion in the time that we expect. If the transaction rate drops, we can suspect that there's something on the system that's causing the transaction rate to drop. Okay, so it could be something in the database. It could be IO counts that have gone through. There could have been a recent change to the application that changed the way that the application works, so that it's no longer using database indexes to speed up getting to the data. It could be that the queries that went into the application are now returning many more rows of data, and that could be slowing you down. There could be synchronization problems like through locks or enqueues on the system that's blocking things from moving forward. But the KPIs themselves that we're looking at, small number, easy to monitor, low overhead on the system to keep track of these, and yet they give you a wealth of information about what's going on your system. Okay. So we look at what artificial intelligence is going to be able to bring to us. So if we look at what machine learning can do, the first thing that we're going to look for is determining what's normal for our system, right? In the past, certainly when I started in this business, everything was kind of a guess. Here's what we want to achieve. Here's what we're looking for. It was really we didn't really do much to determine what is normal expected performance profile for any given application. So by using machine learning, by using some of the statistical techniques and some of the other techniques, we're going to be able to set that baseline. We're going to know what's normal. We're going to know the range of the variance within that data, and what would we expect to be seen for any of the numbers that we're looking at. We're also going to be able to detect that early deviation from normal, so we can start to see an inflection point, and perhaps any of those KPIs that we're looking at, whether response time is now starting to suddenly grow. What's going on? It'll give us an indicator that we need to look at something. And again, because we're looking at an aggregation of multiple transactions, it's showing us something that is more inherent in the system than in any particular transaction execution. So we're looking at the averages changing, not any specific, and that's very important to be able to detect this early deviation. Once we have the KPIs, we can see which one has anomalous behavior, and then we can drill down into that, and we can start to look at the other metrics on the system that are related to that. The KPI gives us an indication of where to start. So, if we know that it's in kicks and it's a transaction, then we can look at the various metrics specifically associated with transaction throughputs at that time, and we can ignore all the other metrics on the system. So it really narrows down the range of possible causes that we need to look at. Certainly, there's this indication of future performance characteristics. If we can start to track the trends of the performance behaviors that we're looking at, then we can determine, hopefully in the near term, where we're going to start seeing problems, and we can be proactive and take actions against getting to that point. And again, we do that by looking at the KPIs, looking at the KPMs, and seeing what's going on in the system. But another really cool part of using these AI techniques is that the functionality that we're using goes beyond performance monitoring. You can use this information or these techniques anyway to do other kind of analysis on your systems, right? You can use these techniques in financial markets, looking at the different characteristics of the markets. You can do it looking at access patterns, as we've talked about before, on the system. That doesn't have to necessarily be performance related, but it can certainly give you some indication, as we mentioned earlier, these problems with protecting data, protecting your system by looking at patterns of behaviors that shouldn't be happening. So this area gives us quite a lot of benefits to work with at what we hope is going to be a relatively low cost. And just to give you an example, here's a screenshot that I took of one of our systems that shows number of anomalies that you can see during a day. These are counts of different anomalies. This is test data, so it's not very realistic. But you can get a sense of what you might be able to see. We see that we have this peak of anomalies at 4 o'clock. We'd want to drill into that, and then we can see various KPIs. For the various KPIs, here's 6 KPIs that are related to that. You can see the contribution of each one of those KPIs to the total anomaly, which is impacting the system that's at this particular application. And we can start to look at other charts. Now, this is a proprietary chart. This is one of our charts, but you can do the same thing, very similar to this, in Elastic and Splunk and Datadog and Grafana or any other visualization tool that you want. You could even do these in Excel spreadsheets. You can use pivot tables and whatnot to produce charts that are very, very similar to this. But this gives you an idea of the kind of insight that you can see by looking at these different patterns. You can see the KPIs that are particularly affected and be able to drill down. And that's where a lot of the power of this KPI and this type of monitoring leads us to. Okay. So, now that we're monitoring, we want to start looking at some more advanced and deeper techniques. We're not doing simple monitoring here. We're doing more advanced monitoring. So since we're focusing on KPIs, we need to really look at the data over intervals. So again, instead of looking at individual records, we want to intervalize our data. Intervalizing the data allows us to see patterns as opposed to specific use cases or specific cases of performance degradation. So we're trying to look at at the whole system or the whole application rather than any one given transaction interaction. Okay, and this is going to help us doing our anomaly detection because we're going to compare any new work against what we have collected in the past and created in terms of our baseline. The baselines are going to be very important. We're going to talk more about that in a few minutes. But creating that baseline is really what's going to help us figure out the patterns and any of the performance deviation that we're looking at. And so our goal is to start, identifying any of the deviation from normal that we're going to see and the new data that comes in from that. So, there are other techniques that we can use, and doing some of the deeper dive analysis on these, is where we start to look at the key performance metrics, not the key performance indicators. The key performance indicators point us to an area that needs to be looked at, but the key performance metrics are those measures that are associated and contribute to the value of the KPI. As mentioned earlier, you can look at KICS transaction rates as the KPI. And what are the metrics that are that? Well, it's CPU utilization, it's IO counts, it's the lock delays, it's it's any of the network bandwidth issues, it's things that are going on in DB2. In terms of there could be problems with some of the access methods or within DB2. The way if you look at some of the isolation levels, things like that within DB2 that are slowing you down. Perhaps you just you have a new application, you did your bind, didn't do your stats, so you haven't updated the optimizer within DB2 to have better access to the data. So we want to start looking at all that. And one of the things that we know from statistics and other measures is that we have these very large numbers of transactions within these intervals, and it's really going to help us understand that we have a true trend deviation away from normal for each one of these applications. So it's going to give us a much better insight into what's going on holistically with our applications of the system than we would have using some of the other standard techniques. So I just wanted to take a moment to kind of just go into, at an extremely high level, what is machine learning and how does it work, and what is it really doing? So most of the techniques that we're going to use, there's two basic techniques that we're really going to talk about today. And one of those is a sort of traditional statistical regression technique. I don't know how familiar you are with statistics, but basically we're just going to do some linear regressions. We're going to calculate some of the means and variations of the data, and that's going to help us understand where to recognize the deviant data. We're going to talk about some of the pros and cons about that as well. But for the other algorithms within machine learning, and this is most of the other machine learning that even you may have heard of, and this is including some of what goes on with some of the large language models like ChatGPT. They're using some of these techniques under the covers in various different combinations to do the ML work that they need to do. So one of the first things that we have to do is pick the algorithm we're going to use, right? A lot of the machine learning today uses these mainly multivariable analysis, especially things like the large language models. They're using an extreme number of variables in their data. But the basic algorithms use one or two variables to determine to set the model. Okay, so what we're trying to do is understand what kind of equation we want to apply to the data, and then we're going to do a minimization analysis on that data. So we're going to look at great large numbers of records. We're going to look at a lot of data, and we are going to do what we can to find the least amount of error between the calculations that we're doing and what we expect to see. Okay, that difference is called a loss function. So we want to minimize the loss function. We want to be able to predict as close to reality as we can without going too far. There, you can overfit the data, which doesn't really, if when you get to an overfitting, it means that you really can't do much more prediction of any new data coming in. We only recognize data that fits the original model, and we just try to force everything into the past and not look at what's going into the future. So some of the key things about minimizing the loss function is that one, it's stochastic, which means that what we are really interested in is more randomization of the data that's coming in. Random data is going to give us better results than non-random data, but we'll talk more about the problem with that here soon. This technique of minimizing the data, minimizing this loss function, one technique to do that is called gradient descent. And if you look at the chart on the right, you can see that really fancy curve. So what we're trying to do is find those low points. We're trying to find these points down here at the bottom that are the minimums. So there's some issues with that. For instance, if you start up here on the top randomly by starting at this point and you try to walk to the nearest minimum, you may end up in this minimum, which isn't the lowest. It has more of an error to reality than does say this point. This point at the bottom here would represent us being very, very close prediction to what would happen in real life. And so that's kind of the goal, is to do this. And it's from a machine learning standpoint, it's like, where do you start with the data? And this is kind of the idea that we want to reach that. So if any of you have taken calculus and you remember this, really what we're trying to do is we're trying to find, it's a minimization function. So we're trying to look at the point where the first derivative of this equation has a zero slope. That's essentially what all these things are doing, trying to get to as close to that point as we can. Okay. And our goal, of course, is to really achieve that maximum minimization of the loss, which is a strange thing to say, because that's going to give us better results down the road. And then there's this concept. Bayesian inference is something we're going to talk about just a little bit more, because it's sort of really the basis for what we do with a lot of machine learning. And how we move forward with any of the performance prediction, things like that. So Bayesian statistics, Bayesian inference has been around for a long time, and it's something we use every day. All of us, it's just naturally a way that humans think, and it actually has a real practical application as well. And basically, it just means that we're using what we know from the past in terms of probabilities and likelihoods, things like that, to predict something that's going to happen later on. Okay, so we have this concept of our posterior beliefs, right? You all know that if you flip a coin enough times, you're going to try to reach 50-50. You're going to get a probability of a half heads, one half tails. That's using your past belief because you've done enough flips to know that this is what to expect. So this will give you a probability of an occurrence. It's built upon those past measurements that we've taken. In the case of what we are looking at for this session and for performance monitoring and behaviors, things like that, we're looking at the measurements that we've collected. So we have a database of numbers that we can look at. We use that to establish a baseline. That baseline becomes our posterior belief, right? Then we have the prior beliefs. So that's the probability of an event prior to us actually applying this Bayesian technique to it. And then the likelihood of course, is what we would expect for this value. So just logically, you would expect that your coin flip would give you 50-50. So you have measurements that kind of give you what you really have, what you really detected in the past. You have your theoretical likelihood of this occurring, which is one half. right? And then you can apply that to the data that you've got and what's coming in. The formula at the bottom basically is this. You read that the probability of A given B is equal to the probability of A times the probability of B given A divided by the probability of B. So I'm putting that in there just because it kind of completes the discussion and something may be of interest to you. But it's basically the ratio of the probability of one event given another event times the probability that you're looking for your new data. So that's it. So why is this important? So the Bayesian concept, the Bayesian model of thinking is what we're using for most of the monitoring in the ML space that we're doing today. Okay. What we do is we collect our data. We get a lot of data. We analyze it. We have this where we can create a baseline from that. We compare any new measurements against that baseline. We can apply some additional math to that if we want to be able to really distinguish extreme changes from normal changes. And then we update the baseline. One of the characteristics of the Bayesian model that I don't think I mentioned on the last slide was that you constantly update your prior beliefs, right? Now that you have new information, you can update your belief about the old information, and that's what we do, or we recommend doing anyway, with the current performance techniques that we're using. So one of the normal techniques that people typically start with is using a statistical regression. This is calculating the mean and standard deviation, the variance within the data. That's all a standard deviation is. It's how much is the data spread out from the mean, right? So it's a natural way to start because it tells you what the average value that you would ever expect to see for any given metric is. And it gives you a distribution of ranges for that so that you know what highs and low values are and what you can expect. So before we go too far into the rest of that, and just real quick, discussion, I pulled this chart. It's a really nice little chart. These bands that you see in here give you the measure of the distribution of the number of samples that you would see from the mean. So within one standard deviation of the mean on both sides, you can get a total of 68% or so of all the samples you would ever see should fit within that range. Okay. If you go out to 2 standard deviations, then you can get up to about 95% of all of the samples would be within 2 standard deviations. And at 3 standard deviations, you're up to 99%. So if you collected 100 samples from your system, 99 of those would be within 3 standard deviations. Okay, and that kind of gives you a range of what you might expect to be normal. Now, a lot of statistical techniques start to say that outliers are somewhere beyond 2.5 standard deviations that would be out here. So you kind of you get a sense of that. Now, we'll talk about some of those numbers here in just a minute, because that doesn't really work all that well for us. So this, statistically speaking, the standard normal distribution requires random data coming in, right? It's random samples from a population that gives you this curve, and so that all of the assumptions and calculations that are made within statistics are very much dependent upon that standard. The random sampleness, the random samples that we get from the population. Unfortunately, samples from a mainframe are not normally distributed. They are distributed more like the graph at the bottom, where you have the peak is much more narrow, and it's very much aligned to the left, and you have a very, very, very long tail on the right-hand side that kind of can go out almost forever. So we're like missing the entire left half of the curve that we have here. So this really has an impact on the what we can take away from the statistical methods that we're using, and it's one of the serious deficiencies of using a regression model on the mainframe host. Even assuming a good standard normal distribution for the metrics we're collecting on the host, you're going to see that we may end up with numbers much too large for us to really process to a day-to-day. So what do I mean by that? So if we look at 3 standard deviations away from the mean, as I said, 99% of those of all of the samples we'd ever see would fit within that range. Okay. The issue is that when we're talking very, very large numbers, that means you have a very large number that are going to fit outside of 3 standard deviations in that 0.1%, as you can see from the chart here on both sides, 0.2%, we consider both sides of the numbers, okay? So as an example of that, recently we were analyzing a data set that had 200 million observations, 200 million records, 200 million KPIs within that data. And so at 3 standard deviations, we found 177,000 outliers at that number. If we increase the number of standard deviations that we're measuring out to 20, we drop down to 5,000. But 5,000 is still a fairly large number, right, of things for us to look at. So we have to consider, what does that really mean for what we're trying to achieve here, okay? So we're not really looking for individual transactions that may be encountering a problem, but because we're looking at a population of transactions during each one of these intervals, what it does is allows us to recognize any of the work of those transactions that are operating very far at the extremes. Okay, so the question is, why does any one given minute interval of data, why is it much more extreme than what we would expect? What happened during that minute to push those transactions very far out, away from the mean? So we're going to want to investigate that to understand, what's going on and try to correct that. And so we want to focus on the ones, those transactions are at the most extreme. So we can keep looking at this data until we find something that comes down to a number of transactions, or I'm sorry, a number of these KPIs that we want to handle. So oftentimes we're going out to 30 or 40 standard deviations to focus only on the extreme during this pass through, and then we can keep iterating. So we can do that, and then we can run the numbers again and continue to improve and decrease the number of total transactions that we want to look at, so that we can be effective in doing this. This method will also allow us to look for trends in the evolution of this work over time. So in the chart on the bottom left, this is another example based on some real-time data, where you can see the area that's the shaded area on here, and I guess that's pink, represents the baseline. So that's the mean plus so many standard deviations above and so many standard deviations below. That's probably, I think, at the 3 standard deviation level. And you can see the solid line on there are the real-time numbers, and the real-time numbers fit really, really well to the baseline until you get to somewhere around this point, where it starts to trend high. And as you can see now, we are continuing to trend above the baseline, significantly above the baseline level, right? So the question is why? In this particular case, this has to do with a customer who changed a DB2 program, and so IO counts went very, very high. So the overhead and processing all that pushed the consumption levels extremely high for this particular transaction. Okay, so what we can see here is that this is what I'm calling the evolution of the workload. It was running along normally, then suddenly it evolved. Something changed in that application which pushed it out of the range. We can see that. And in some cases, and I think this may have been one of those, pushing those numbers high was using more processor, and this was had a significant cost impact to the customer, due to the IBM 4-hour rolling average licensing. So by detecting this early, they were able to save significant amounts of money. If this had gone undetected, and this would not be easy to detect, if this had gone undetected, it could have been a significant problem for the company. Okay, so the statistical regression that we typically use is useful, but it has some limitations. We just need to understand what this means and how we can best use that. Okay. Here's another example of that, where again the shaded area is the baseline, and this was some test data that we had run last year, and we had set up some workloads that we knew were going to generate some anomalies, and we had planned for these anomalies and for this one. But interestingly enough, when we ran our test, this guy pops up. This one. That was completely unexpected. So, here's an example of where we were monitoring the system, and we caught somebody doing some testing on the system that we didn't expect them to be doing at that time. They were running some work in a TSO that was consuming quite a bit of CPU at that time. So we were able to catch that. So, using these techniques, and even with this one, which I think had a yeah, you can see that in this case. I think um, the threshold level that we created was up around 30, something like that, which made these pop out. So these are truly extreme cases that would require more investigation. So okay. So what are some of the things we need to be concerned about with machine learning? Okay, really doing machine learning requires a lot of data. Excuse me, 200 million records, 200 million KPIs is not really a large number of KPIs to measure. I think that was roughly a week's worth of data that we collected. So, it takes it's a large amount of data. We need good data, so we have to be concerned about the quality of the data that we're getting as well. It doesn't do us any good to collect data that's not representative of the work that's typically done on the processor. So, collecting metrics at 4 o'clock in the morning on a weekend is not going to be representative of 4 o'clock in the morning, say a Friday or a Wednesday. So we want to make sure that we're looking at the right quantity of data, the right quality of data. And then to process this data with machine learning requires massive amounts of CPU. Machine learning is an iterative process. If you have, and this is one of the issues with especially large language models as well these days, is it can take a very long time and a lot of CPU to process this data. You're looking at it like we were talking about earlier, 200 million rows of data, and you might need to process that data 10,000 times iteratively in order to achieve that minimum loss function with the way machine learning determines the minimum. So you can see that's a lot of processing power to really crunch all those numbers. Okay, so you're obviously not going to do a lot of that on your busiest production systems, right? So you're going to have some processor set aside to be able to do that kind of number crunching. Okay, and you need to be able to choose the correct model for the type of work that you're going to be looking at on here. We'll talk about some of the more models, but one model would be the regression technique that we just looked at, and there's other AI models that can also provide insights that we'll look at in just a minute. Also, the lifespan of your model can be short. So once you've created a model by crunching all that data, within a week or two, that model may not be very accurate or successful anymore. So you may need to change your model and recreate or recrunch all the numbers and create an updated model from that. So it's not like you can do machine learning once and you're done and you never have to come back to it again. You could be doing it quite frequently. One of the techniques that we talked about earlier with the Bayesian technique was updating your baseline continuously. So there, your baseline would continue to change over time because that regression model does not require the full amount of overhead like some of the machine learning models we're going to talk about do. So the large language models, for instance, are some that really require a lot of number crunching. Okay. So just looking real quick at some of these ML techniques that we're going to talk about that do really require a lot of CPU processing power and time are the random forest clustering and k-nearest neighbors that do that. Basically what these techniques do is they're looking at all the data points and they're trying to find, in a way, you can think of it as finding patterns within the data. If we were to chart that, you'd see a cluster of data points in one section, another section, et cetera. And so, random forest clustering, k-nearest neighbors, all of these result in, in localizing or finding all the data points that are close together, right? So you could think of that as from, in the regression method where we talked about the number of standard deviations from the mean, it's kind of the same thing as that, but we may be looking at several lines. For instance, in a random forest, you could have 10, 20, or 100, different clusters of data within the model. And so the idea is to find new data to see where it fits closest to each one of those different clusters. Okay. So there's different types of random forests. There's different types of some of the clustering techniques. And the k-nearest neighbors is again, it's a similar type of process. All of these have slightly differences in the algorithms and the calculations that are done, but they all end up basically doing the same thing. They're using a loss function minimization technique, and they're trying to find where the different regions of clustered data exists. So here's a few examples of this. The isolation forest that you can see on here. This is a variation of that random forest variant that I talked about earlier, just a few moments ago, right? And very fast, very efficient, given the large data sets we have. You end up with tree structures that can scale out and gets it really quick to get to the data that you want. So the distance from the top to the bottom is something on the order of the log of the number of entries that you have. So it's really the number of levels down that you need to get to find the data that you're looking for in the tree. Okay, and then you have local outlier factor. Again, this kind of is a variation of the k-nearest neighbor. The k-nearest variant is one where we're looking at a cluster and we're looking at the nearest, say, 10,000 data points that are close to that. Okay. So you can use these techniques to find the data that is significantly different from what the expected values within the data is. Okay. PCA is the principal component analysis anomaly detection. This is an interesting one in which they basically run through the vast large arrays of numbers, the vectors, and they create the model, and then they try to recreate the data from the model that they created, and then they look at the difference, and that's your loss function. And you're looking for the maximum difference between the original value and the new value, and that kind of points out your anomaly there. So each one of these can be much better at finding true anomalies, true anomalous and true deviations than does the standard statistical regression model. But these do also require far more computation to create these models at some point. And even though they're fast and efficient, once the model has been created, it still takes quite a bit of processing power to create these models. So they're very, very useful. They give you very, very valuable information. And we just need to find the best way of creating the models from these over time. So here's an example of the PCA anomaly that I was talking about. So you can see how we have data clustered up here at the top. All these data points are all clustered together. And from this plot, you can see the outliers that were found, closer to the bottom of this thing. So these are these data points are the ones that you'd be the most interested in examining to understand why this value is so much lower, so far away from what you would expect from these response times up here. Okay, so this is very useful. And it's really great to be able to see this on a chart. What would be wonderful is that if you could, have this information pulled out and provided to you. So, there's a little bit of software that you can run that will allow you to, be alerted as it's running through these numbers to be able to find these different points as they pop up. And as new data comes in, you're going to still see that it's significantly, distant from the data. So you can be notified very early, and that achieves our goals of being able to have an early response to any of the deviations in the, in the access. So I found this particular chart a long time ago. I find it really useful. It's just kind of a good mnemonic eye catcher way of seeing the different types of machine learning that there are. And understand this is just the very tip of what's available to you. There are hundreds of different models that can be used, and they all provide something a little bit different. And this doesn't really go into much of the deep learning neural net type algorithms that there are. That those are typically used by the large language models and some other decision trees like that. So I put the link down at the bottom. This is from Scikit, and one of the interesting things about this that I encourage you to do is go to this site, and any of these boxes in green on here are links to more information about that particular type of regression model. So the blue circles on here, or the blue ovals, are you can think of this as a flow chart or a binomial tree to help you identify the type of activity that you're looking for. All right. So we haven't talked about unsupervised and supervised models. Some of these are like, if you have labeled data, you can get to supervised. If it's unlabeled data, it's going to be unsupervised data. So there's a lot more depth to the machine learning than what we've covered today. Some of the other things that we really haven't covered at all is the type of data and things like that. So that's some other areas that clicking on these and doing a deep dive into these techniques can really help you understand better. Okay. So, looking at what we've done here, looking at these different AI techniques, looking at this data can, help us identify the areas in these systems we really need to look at more. We can get down to very specifics, and we can also start to look at the downstream impact of this. We know the KPIs. We know where they're coming from. We can associate those with transactions, and we can understand that as my transaction changes over time and it's now performing outside of the original normal bounds, what impact is that going to have on additional work on the system? So, transactions don't operate in isolation. Many times, one particular customer request may result in multiple transactions being executed within, a CICS region, for instance. And so if one of those transactions has some sort of delay, that's going to impact the rest of that. And it may also have an impact on the other work going on in the CICS region. So nothing is really working in isolation here. So we want to be able to understand what those impacts are. So one of the things that we can also do with the AI techniques, especially I think some of the clustering techniques, is we can start to look at workloads that are running together on the system, that typically run together on the system, and understand the impact that one poorly performing application will have on another. And we want to be able to correlate all that data across the tech stacks. So I have a transaction that may come in from the web, hits the CICS transaction gateway, goes into CICS. CICS starts making DB2 requests. So we have activity going on in a DB2 region that is going to impact the performance of that CICS transaction. CICS may also have something going into IMS and pulling data from there, or ZOS data sets. And it could also be, hitting, MQ and other systems like that. And we really need to understand how all of these different systems tie together. And again, using some of these AI techniques, correlating the data across these different systems are going to give us that maximal insight, into the performance of our applications. So that's what I had prepared for this today. I thank you all for attending and listening to me. I hope this was helpful for you. If you have any questions, feel free to ask now, or if you want, you can reach out to me at here's my email address at Rocket. So feel free to reach out to me anytime. I'll be more than happy to respond to you. And just one more comment, please provide session feedback. I'd be very interested to know whether you found this at all helpful, interesting at all. And thank you for your time today.
Thank you, Rod. That was absolutely fantastic. I mean, hearing statistics, I was like, this is taking me back to, going back to university. I was
Mhm.
like it's one of those things where it's like sometimes you kind of forget about all the mathematics that go into it, and all these different parts. And seeing it, and it's just like I was just like, wow, yes, okay, this is fantastic. This is exactly what I'm looking for. So, I mean, I'll definitely be rewatching this session again, sort of thing, to go through all those details, and we'll definitely be reaching out to ask a lot more questions. So, I'll apologize in advance for pestering you in the future regarding it.
Quite all right.
I don't know. I mean, you're getting the thank yous from the chat, sort of thing, saying that, thank you, sort of thing. I don't know if anyone has any questions. If anyone does, by all means, like I said, far away now. If not, of course, reach out to Rod, like I said. He left his email in the presentation. Yeah, and please, of course, don't forget to provide some feedback. Session code is 4H, so please all don't forget to provide some feedback.
Okay, great. Well, thank you all.
Cool. Well, thank you, Rod, and thank you everyone else. I hope you all have a great day, and take care, Rod. Thank you once again for doing it so early in the morning for yourself.
Absolutely. All right.
All right. Cheers, all.
Bye.
Bye bye.